Hello, welcome. In this video I'm going to be telling you about the polynomial factor theorem, which is basically connecting the factors of a polynomial to its zeros. So the theorem is that x minus a is a factor of a polynomial p of x if and only if p of a is equal to 0. And now we've already seen this a little bit. We've seen the connection between factors and zeros of a quadratic polynomial. Okay, so we saw if p of x was something like, x squared plus 3x minus 4, and we were able to think of two numbers that multiplied to negative 4 while adding to positive 3, we were able to factor this thing. And I think those two numbers were going to be positive 4 and negative 1. So I could rewrite p of x as x plus 4 times x minus 1. We didn't, at a certain point we kind of stopped giving it much thought. We just knew that, okay, positive 1 and negative 4 were going to be the zeros. Actually, I'm going to draw the graph of this thing first before I commit to the location of any zeros. Okay, and so we had positive 1 and negative 4 were the zeros of the parabola. But the reason we knew this was that, a zero, like these points right here and right there, those are places where y equals 0, where p of x equals 0. And we also know about the zero product property, which is that, if two numbers were multiplying together to equal 0, then it's because one of them was 0, right? We're not going to multiply two non-zero numbers together and get 0. That's not going to be possible. So we said either x plus 4 was equal to 0, it was the 0 number, or maybe x minus 1 was the 0 number, and that led us to believe that x was negative 4 and x was positive 1. So we've seen this connection before between factors and zeros. But if we're going to be plugging in a lot of x values into a lot of polynomials, we need a kind of a quicker way to do that than just grinding through the arithmetic. Especially with some of these higher degree polynomials, sometimes the powers, there can be a lot to deal with. So I'm going to show you about synthetic substitution. Okay? So we've seen function notation before. We've plugged in on a function. So if p of x is 3x squared plus 4x minus 5, and we want to talk about p of 1, we're just going to replace x everywhere we see it in the equation with 1, and then we're just going to kind of do our arithmetic and find the value. If I square 1, which I need to do before multiplying by 3 because of PEMDAS, and if I square 1, I'm going to get 1. So I'm going to have 3 plus 4 minus 5 is going to equal 2. But then let me also show you that what happens if I run 1 through the structure we had for synthetic division in a previous lesson. And if I go over here and I run this through, maybe I'll switch up the color, drop it down, multiply, add, multiply, add. Okay, this number I get right here, this is the value of the function. Okay. So, because that was a pretty nice algorithm we had, and it helps to keep the numbers smaller and it keeps you from having to take any powers of any numbers, I'm going to recommend you use synthetic substitution when you're evaluating a polynomial. Okay. Just in general in this class. That's how I'm going to be evaluating polynomials most of the time. Maybe not a quadratic one. But I'm going to show you how this works in general before I move on. Okay. So for, A, B, and C, if I run x through there, if f of x equals, or, if, basically I'm trying to show you it's going to give you ax squared plus bx plus c. I'll just tell you. So I drop this down. I got a, I multiply them together, I get ax, add these things together. Okay, since b does not have an x attached to it, it's not a like term, so I'll have ax plus b. And then if I was to multiply that by x, I might remind you off to the side that if I'm going to multiply x by ax plus b, I have to distribute to both of these things. So I'd have a and 2 powers of x, and b times 1 power of x. And if I added these things all together, I'd get ax squared plus bx plus c, which is what I would expect. Right? Maybe we'll work a quick example. So we're going to use synthetic substitution to evaluate the function at the given x value, and then I'm going to take it a step farther. I'm going to determine whether, a corresponding factor is a factor of the polynomial or not. So I'm going to start with, okay, find f of negative 1. We can do that. So I'm going to copy in the coefficients like I'm doing synthetic division. So 1, 2, negative 3, 1. Okay, I don't have any missing powers of x, so I don't have to worry about any zeros or anything. And I'm going to run negative 1 through here. So I'm multiplying and adding, multiplying and adding. Okay. All right, let me just double check. Okay, I like to do that when I run something through synthetic. Just run it through first, with pencil and paper, and then the second time mentally to make sure everything looks right. And, yep, looks right to me. Okay, so that means f of -1 equals 5, and also the binomial x minus -1 is not a factor of f, specifically because f of -1 is not 0. And then if I was going to do this one, I've got 1x to the 4, -2x to the 3. Okay, I've got no x squared, so I need to put in that 0 for a placeholder. Positive 5x and -3. I'm going to run 2 through here. Okay, drop down the first number, multiply, add. Multiply, add, multiply, add. Oh, okay. And add again, and I'm going to get 7. And just like on the other one, I'm going to say, okay, g of 2 is 7, and as a result, x minus 2 is not a factor of g. Okay, I kind of thought one of these was going to come back 0, and I was going to be able to say it was a factor. But I wrote these notes a long time ago, so yeah, you know how that goes. So, all right, a new set of examples. Is this thing a factor of p of x? Okay, so is x minus 3 a factor of p? So we're going to set up for synthetic substitution. So I'm going to copy in my coefficients. 1x to the 3, -2x to the 2, positive 2x, -15. And if I'm checking x minus 3, I'm going to run 3 through synthetic division because, you can look at it as substitution or division. If you're thinking about synthetic substitution, you're using the factor theorem. If you're trying to use synthetic division, well, then you're going to see if it divides cleanly or not. But it's really the same thing, same idea. So I'm going to drop this down, multiply, add, multiply, add, multiply, add. Okay, now, because I got 0 for my remainder, I know that yes, x minus 3 is a factor of p of x. Okay, but I've got more to say about this. When we learned about synthetic division, we saw that these numbers that were along the bottom, that weren't the remainder, these were part of our quotient too. So I'm going to say that p of x can be written as x minus 3 multiplied by, the quotient there that I'm going to get. It's going to start with 5 because there's no remainder. There's going to be a positive 1x, and there's going to be a 1x squared. Okay, so I can further factor p using the fact that I know that x minus 3 is a factor and synthetic division to get myself a fully factored version of p. I can tell that x squared plus x plus 5 is not going to be able to be further factored because I can't think of two numbers that multiply to 5 and add to 1. All right, now maybe you try this on your own. So I'm going to ask you again, is x minus 3 a factor of this polynomial? P of x, where P of x is x to the 3 minus x to the 2 plus x minus 6. Okay, so you try this on your own. Do the same thing I just did. And then you can check your work against mine, which is going to pop up on the screen here in just a couple seconds. All right, there you go. So I ran 3 through synthetic substitution. I found that P of 3 was equal to 15. And I concluded, as a result, that x minus 3 is not a factor of p, right? Because in order for it to be a factor, it would have to divide cleanly. I would have to see a remainder of 0. I would have to see p of 3 equals 0. But I'm not seeing that, so it's not a factor. All right, now here's a good example. I like this problem type. So we're going to find the value of k that makes x plus 2 a factor of the polynomial p. Okay? So what we're going to do, we're going to run -2 through synthetic substitution. And we'll kind of track it in, I guess, in terms of k. We'll just run synthetic substitution as if nothing is wrong. Nothing wrong with putting a k of a letter in synthetic substitution. And then we'll just make sure that whatever we get, we'll set it equal to 0. So we have a remainder of 0, and then we'll know it's a factor. Okay, so let's get to it. So let's say 2x to the 3, 5x to the 2, kx's and negative 10 divided by kx plus 2, so I'm going to put negative 2 in there, drop it down, multiply, add, k minus 2, that's k minus 2. Now if I'm going to multiply k minus 2 by negative 2, I'm going to do that off to the side so you can see what I'm thinking. I'm going to multiply, that's negative 2k, and negative 2 times negative 2 is positive 4. I'm going to multiply negative 2 by both of these things. So I get negative 2k plus 4. Need some more real estate there. I'm going to add those two things together, and okay, the k's can't go with the numbers, so I'll just have negative 2k plus 4 minus 10 would be minus 6. Okay, and if x plus 2 is going to be a factor of polynomial p, then if I divided p by x plus 2, I'd have to get a remainder of 0, or factor theorem says that I would need p of negative 2 to equal 0. Either way, that means that this thing in the box, this negative 2k minus 6, needs to equal 0. Okay, and then this is the type of equation that we're going to be able to solve. So we're going to start by adding adding 6 to both sides and dividing both sides by negative 2. And there I've got myself a value of k. And then you can check that if you want, plug in negative 3 for k and run negative 2 back through synthetic substitution, and you'll see that you'd get a remainder of 0. Alright, now the main problem type we're going to be encountering here is, here's one factor, find me the rest. And this one works really well for like a free response type question. So I'm going to do one of them for you, and before I even start, I'm going to point out that this one's already factorable. We could do group and factor on this. But I'm going to kind of just use this one to show you how it works, and then I'm going to ask you to try the rest of them on your own and check your work against mine. Because this problem type, if you're going to have to produce your own work on, say, an assessment or quiz or a test, then you got to start practicing, and you got to start practicing immediately. So let's get to it. So I'm going to start by dividing the polynomial I'm given by the factor I'm given. So 1x to the 3, negative 3x to the 2, negative 9x to the 1, and to 27 divided by x plus 3, I'm going to need to put negative 3 in there. Okay, so I'll drop it down, multiply, add, multiply, add, multiply, add. Okay, sure enough, this is a factor. And then I say, okay, I've got x plus 3, that's one of my factors, and then the rest of it is going to be, well, just this quotient I'm left with here. And so if it helps, if you have a hard time with it, start from the right. Okay, that 9, it's just going to be 9, right? And then the powers are going to ascend from there. So I've got a positive 9, a negative 6x, and a positive 1x squared. Okay. And then you're going to have to say to yourself, okay, this thing that I just got, is it itself factorable? And x squared minus 6x plus 9 is indeed factorable. I can think of two numbers that multiply to positive 9 while adding to negative 6. That would be negative 3 and negative 3. So I've got x plus 3 times x minus 3 times x minus 3, which could just write like that. Okay? So you're going to, with this problem type where you're given one factor and you're asked to find the other factors, you're going to start by running the first one through synthetic division. You're going to look at the quotient and kind of have that as one of your factors, and you're going to see if you can factor that anymore. Okay, so let's try this. All right, this one also looks like you could hit it with group and factor, but I think I'd like for you to try this one on your own, because this is going to use one of our new factoring types that we just learned about last time. So this would be perfect for you. It's right at your level. So work this one on your own with the video pause. You're going to run it through synthetic division. You're going to look at the quotient and see if that itself is divisible. But then you can check your answer against mine in like 5 seconds. All right, there you go. So I went and ran it through synthetic substitution or synthetic division, and I was left with x minus 4 times x to the 3 plus 1. And now another thing I kind of forgot to mention don't know, any of the other times I've been talking to y'all about this, is that if you're having trouble with like kind of the place values here, you can start, okay, with the remainder. Well, we know the remainder goes over the divisor. Okay, then it's the constants, which I might call x to the 0, because I'm trying to remind you that the 0 power of a number is equal to just 1. Then we've got, ascending powers of x to the first, x to the second, x to the third. Okay, so that's where I got 1x to the third plus 1. That's a sum of 2 cubes. I can factor that more. Okay, and that's one of our new types of factoring, and that is one that you are expected to know, that formula for that. So, what better way to learn it truly than to just keep using it kind of day in, day out. Okay, so that one was good, but let's do another one. All right, this one is perfect, I think. So I like this one because it's one that you look at and you wouldn't be able to factor it already, right? We don't really factor fourth degrees or things with 5 terms in them. That's not really something we've got in our bag. I don't know that I would know how to factor this one besides being told that x minus 1 was a factor. So what we're going to do, maybe I'll do this one. This video is not going to be very long. So I will copy in the coefficients 1, 2, x to the 3, negative 7x to the 2, negative 8x to the first, positive 12, and I'm dividing by x minus 1, so I'm going to run 1 through synthetic division, 1, add, multiply, add, multiply, add, multiply, add. All right. And I see a remainder of 0, so I know that this divided cleanly, and I have x minus 1 multiplied by, okay, this is going to be my quotient here that I'm highlighting, and we'll note this is some number of x to the 0s, x to the 1s, x to the 2s, and x to the 3s. So I'll have 1x to the 3 plus 3x to the 2 minus 4x to the 1 minus 12. Minus 12 could be written as minus 12x to the 0 because x to the 0 is just 1. Okay, and then this thing here, this factor that I've just highlighted, it's going to be factorable by group and factor. So I'm going to say, what can I factor out the first two? An x squared. And I'm left with an x and a plus 3. And then the second two, I can factor out a negative 4. And then I'm left with an x and a plus 3. That's a good sign. And then I can factor out the x plus 3. And I'll be left with x squared and minus 4. Okay. I feel like I need just a little bit more room. And because I can see that x squared minus 4 is a difference of 2 squares, and that's something I can work on also, right? X squared minus 4, okay, it's going to be x plus 2 times x minus 2. Okay, and that is a fully factored polynomial. What I'm going to leave you with is just like a little bit of commentary here. I don't know if I've said this yet or if we've really kind of touched on it yet, but when we studied quadratics, we only ever had at most 2 factors, right? And so now that we're looking at a 4th degree polynomial, we would have at most 4 factors. We can't have more than 4 factors, but see, we are having exactly 4 factors here. So that's something to think about as we move forward. But that's going to be all for this lesson. Thanks for watching.